Hi, I'm Garrett Richards, and this is Lab Group 3A. So in this lab, we started off with the same Keplerian beam expander that we created in the last lab. Essentially what we did was we aligned this laser to the rail, and then we aligned the microscope objective with the laser. Once we had the microscope in position, we stepped out. We started with a large spatial filter and started to step down the spatial filter to 25 micron, which is appropriate for our 0.4 numerical aperture, 8mm focal length microscope objective. So after that, we created a Keplerian beam expander. The distance between the collimating achromat lens and the microscope is the sum of their focal lengths, so roughly 258 millimeters, because we chose a 250 millimeter focal length achromat. You can see that this is an appropriate focal length for the numerical aperture of the microscope because the beam completely fills it. After that, we verified collimation using a shear plate. We separated the shear plate by, an okay distance, just to give us some working space. And in our first measurement, we were measuring the focal length of the low power mirror here. So we made sure that everything was aligned with the mirror, and then we flipped the shear plate around and noticed that the fringes are rotated clockwise 67 degrees in this orientation. The fringe spacing is 4 millimeters and the shear distance is 9 millimeters. And let's see, when we move the mirror back about 1.5 meters, you see that the wavefront separation in the shear plate is caused horizontally by the shear distance and vertically by the wedge angle. And we measured the changes in the fringes. So it went from 67 to 50 degrees rotated clockwise, which indicates that we're still inside focus. It went from 4 to 2 millimeter fringe spacing, and from 9 to 7 millimeter shear distance. Using these numbers, we should be able to calculate the radius of curvature of the low power mirror. And this sort of derives from the fact that an incident spherical wave on the shear plate, the fringes will still be straight and they will be perpendicular to the direction of separation of the wave fronts. So by measuring these parameters in two locations, we'll be able to determine the power of the mirror.
Hi, I'm Red, and I'm going to be talking about part D. So in this part of the lab, we put a test lens in between our collimating lens and our shear plate. And the reason we did that is we're testing refraction and not reflection. So it's going through our lens into our shear plate. It's very similar to the first part of the lab. So we can use the fringe orientation to determine the focal length of our test lens. So in this case, if you get up close and look, you see our fringes are very straight, which is nice. It shows that we have a perfectly spherical or close to spherical wavefront entering our shear plate. And for the wavefront separation, the horizontal orientation is determined by the shear distance, and the vertical orientation is determined by the wedge angle. And with this, we're rotated a little bit clockwise, so it shows that we aren't quite collimated, which is true because we have a lens in our system. So we can use these measurements that we've determined to find our focal length.
Hi, I'm Jordan, and for the last portion lab we were measuring the radius of curvature of a test mirror here. So we had the same setup as before up into the shear plate. We rotated it 180 degrees, and we have a reference lens here of some unknown focal length, and then our test mirror here. So what we're going to do is we're going to start at position 2, and I'm going to show you that we actually do have fringes on our shear plate, which tells us that the light traveling back through the system is collimated, and that is because the wavefront curvature coming out of this mirror is perpendicular to every point on the surface of this mirror, and that the wavefront is also the same curvature as the mirror itself. And so we can see here, when we translate the lens back towards the reference, or the mirror, sorry, translate the mirror back towards the reference lens, we can see the fringes change, and we're going to come through a focal spot right here, and that basically is 2F, 2F, so a 4F system from object to image. And we can translate even more towards the reference lens. until we reach this point right here. And now we are at the front focal point of the reference lens. We know that if we place any object at the front focal point of a lens, that it's going to become collimated out, and that is why we have the fringes. Also, the fringes do have some curvature to them, which tells us that there is some curvature in the mirror. So it's probably not hitting a plano side, and it's probably biconvex, if anything, because otherwise, if it was plano convex, we wouldn't see fringes at position 2, or we wouldn't see wavy fringes at position 2, and we did. And we also saw them here as well, so that is an indication that it is biconvex. And the radius of curvature that we measured is 200 millimeters, which is a focal length of 100 millimeters. And